contains the information of the license provided by the synopsis, okay, and the path where your Centaurus TCAD is being installed, right? So we need to call that, software. Therefore, we require some path, right? That is given by this. Hit enter again. So you got a very nice welcome. Welcome to Synopsys EDA tools. So over here, we have already learned that in order to open the Centaurus structure editor, what we need to type? We need to type SDE simply. Hit enter. So we have a nice window over here. Okay. So before jumping right into the drawing part, let me fix some default settings. So we don't, in the draw section, you just deselect this auto region name. Because we don't want to name the regions automatically. We want manual. So deselect this. After that, we want exact coordinates. Select this. Okay. And then, in order to record all the commands coming in this window, what we need to do is we need to go to the file, journal on, and give a name over here. Say maybe NMOS, right? Open. Okay. Just keep it like that. Let us start. Please make sure that your direction over here is, in that direction. Not necessarily, but for our convenience, let us do this. So in order to do that, you come to View, GUI mode, and 2D, right? And please select this one. So your X is in this direction, Y is in this direction, which is exactly matching with our proposed device, which we are going to demonstrate. Okay, fine. So far, so good. Right. Okay. So let us now draw the substrate. So that's why a silicon material is selected by default. Okay. Rectangle is selected. Just left click and drag and drop. So this is the first vertex, which corresponds to this particular point. So your X will be 0, your Y will be 0. This is the second vertex. Your X will be 1.5 and your Y will be 0.7. Okay. So just type in over here 0, then 0, then 1.5, then 0.7. And hit OK. Here, you have to enter the region name, and the region is what? Substrate, substrate, right? Okay. So we got a nice rectangular substrate of silicon, right? Okay. Next, we want to include the source and the drain region in the same substrate. In order to do so, we need to select this thing, which is new replaces all. Okay? And then what you're going to do is just you want to draw a rectangle, right? So this is the rectangle, right? So you want from 0, 0 to 0.25, 0.1. Okay. So this is the source. Okay. So the source is created. As you can see over here, these are the 2 points which we have taken, 0.25 and 0.1 and this point, right? Same thing applies for the drain also. Draw like this. So the X point will be 1.25, 0, 1.5, 0.1. Okay. So this is DRAN, drain. Okay. So we have nicely created both source as well as drain terminal. Or to be more precise, The two regions are created. Okay? So our next intention is to provide an oxide layer on top of the substrate. Okay? So in order to do that, we need to select a silicon dioxide. Because silicon dioxide is a more, it always offers without doing anything. It oxidizes, So in order to do that, we need to draw, right? So the first vertex, we will start from the source side, so 0.25, 0, and then 1.25 and minus 0.005. Why minus? Because we are going above the x-axis, and above the x-axis I have taken y to be minus. Understood? So it is like this. Okay. So okay, and the reason will be, say, let us say T-ox maybe, right? Oh, this is the oxide, and the thickness is 0.005 micrometer. As you can see clearly over here, the SiO2 is deposited, right? We will not physically include the metal over here. That will be done by using the electrode. That will done the job, right? Okay. So in order to include the contact, we need to add two vertex on the source side and the other one on the drain side. So in order to do that, please go here, edit, 2D edit, add vertex. This point, it will be your 0.2 and 0. This thing, okay? You can see over here, and the same thing applies again, 1.3 and 0. Okay. So the two vertex has been created. Next, as we already know that during the diffusion process, these things will not remain in the actual fabrication scenario. It will be some in the form of arc maybe, right? So we don't want it to look more ideal. So therefore, in order to make it more realistic, what we're going to do is we're going to make it, an arc sort of figure. In order to do that, we need to select this particular vertex. In order to do that, please select vertex from this particular drop down and make sure it is on, and just click over here, and you got an orange color over here, and then you go to the edit, and select. You type the radius to be 0.1 and hit OK. Boom, you got a very nice shot of source region. And the same thing applies for the drain side also. Here, and 0.1. Boom, you get this thing. Right. So we have nicely made the source region, the drain region, and the body, or to be more precise, substrate. Right. So we want to make it separate. How to do that? Because we are going to dope it with a different dopant. Right. So in order to do that, please come to edit section and press separate lumps. That's it. After that, we will go to device, constant profile doping, and first we will dope the substrate. So please select region 1 substrate, and the substrate region is highlighted. Okay, and please write here dot substrate, constant profile placement dot substrate dot substrate. It will be boron active concentration 1E plus 17 at placement, right? The same thing applies for source. So while you are selecting the source, it will select this area only, right? As you can see clearly. SOURCE source. The same thing applies over here, SOURCE source, and it will be phosphorus because it will be heavily doped N++ region. So let us make it 20. Right. So this is source. At the same thing applies for drain. Just change the name of the placement, that is drain. That is drain. Hit OK at placement. Okay, done. We are done with the doping profiles. What is next? Next, we are going to add the contacts. In order to do that, we need to select contacts. Contact sets. So you will encounter some type of window. First, get 100 for get. Okay? Set. And it will define over here get. Next is SOURCE source. Make it say 11. This is the color code, okay? 110 is the color code. It will have a particular color. Set drain 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 may just make it 111. Look nice, okay? Next is the substrate. Right, in substrate make it 0, 1, 1. Okay. So all these things will be available here. Okay. So what we are going to do is, since these are edges, in 3D it will be fast. Okay. Since these are edges, what we're going to do is we have to select the edge. Okay. Make sure this is always on, and get, select over here, contact, set contact. Same thing applies for source region. Select over here, contact, set contact. Same thing applies for drain region. This, and same thing applies for the substrate also. Please select substrate from here. Substrate, contact, set contact. So the device is now fixed. The only remaining part is the meshing part. Okay. So in order to do that, please come to the mesh section, define evaluation window, and pick a rectangle. Right. So rectangle, you can give any size of the rectangle, so that provided everything comes under that particular window. So, but we will do it in a more precise way. So 0 minus 0.005, and it goes from 1.5 to 0.7, right? So make it all, because this is covering all the device. 0 minus 0.005, okay, everything looks good, hit OK. So the entire device is covered with this particular meshing window. We need to define the meshing sizes, right? Like number of horizontal lines, number of vertical lines, and that will give you the meshing point where your Poisson and the continuity equations will be solved self-consistently, right? And next will be mesh, and in the mesh section, please come to the refinement placement, and please select over here all, right? Refinement dot all, this thing dot all. So in the x direction we have chosen to be 0.02, 0.02. If you make it more smaller, then your meshing will be very fine, and it will take much time in simulation, so it is a reasonable amount. So 0.01, 0.01, right? Create. TCAD. Then next is this is our intended area. So let us try to create another one more window over here, multi-box placement. So this is the channel region defined from where to where, from 0.15 to minus 0.005, 1.35, 0.1 define, and the channel OK dot channel maximum is say 0.01, 0.01, 0.005, 0.005, 1, 1.35. Okay. This is just the parameter, like up to which you would like to make it, like the distance between the two lines and all these things. Right, you can give it in whatsoever you want. Okay. Nothing rocket science over here, and you get this and add placement and close. Everything is going fine right now, so we will perform meshing. Build mesh, we'll change the name to NMOS. Build the mesh. So once it is done, it will show successfully over here, meshing successful, right? And the meshing is done, and automatically your as visual window pops up, and you can see the device over here. In order to see the meshing, you can click over here, right, like this. So you can see fine meshing over here in the channel region, right? So right, like this. So this is the points where your transport equations, the Poisson equations is going to solve, right? Perfect. So this is the device. So once it is created, you just close it, and what you have to do is you can save it, right? So Control S, you can save with your name as NMOS, save. Okay, and remember we have already recorded this. In order to make it stop, journal off, file, journal clean, select the already existed file, open. Right, so the same thing appears as in the simplified form. So it is the record of what you have done. Okay? So you can make it variable type of sort of program, maybe over here 1.5 can be written as X, Y, and something like that. That is beyond the scope of this tutorial. You can close it. Now the work of SDE is completed, and the job of SDE was to provide NMOS mesh.ttr, right? So this is the file which is needed for further, further process, right? So the simulation will take a lot of time. So what I will do is, I have already simulated the same thing, so I'll just show you that file. So one more file is, just copy this file and I will let you know. These files will also be available with you. So basically this is the S-device environment. In the S-device environment, you will have this file section, Electrodes Section. These things are already available in that this PowerPoint presentation. Please read it very carefully. Your doubts will be addressed in the later stages. We have Physics Section, we have Math Section, we have Plot Section, we have Solve Section, right? Every section has individual roles, right? Here you have Fermi direct statistics is being defined over here. So the metal is being defined as 4.24. So it corresponds to the particular metal whose work function is 4.24. Right. So it comes to be maybe TiN, maybe, right? Titanium nitride. So all these things, right? So here, this is the NMOS mesh TDR. This is the file that you need to be provided, right? And how are you going to run it? I will explain you. In the PowerPoint, we have already defined that it should be S device, right? And the name of this, name of this file, that is NMOS demo, something like this. NMOS demo, something like that. So I have already done that. So maybe somewhere NMOS design 2. And you just hit enter, and then it will keep on running these things. So okay. So one error is coming over here, and the error is in this in this NMOS I have already defined in the small letter. The name should be similar, right? It should be S. It should be in. It should not be in the capital letter. Before this tutorial, I have simulated in the capital letter. So it should be same as you have already designed in the SDE environment. Okay, this should remain the same. This will be drain. This will be get. This will be get. I think it should work now. Right, it works. So it will keep on running. So it will take time. So since the presentation is going, around 30 minutes, so I just want to make it run in this, and I'll just show you the results which I have already obtained. As visual. So there are two types of file. One is TDR to look the picture, to visualize the picture. For example, maybe this thing. This is the picture that I got. And we want to see the doping profile, maybe. Doping concentration. The red one is 1:220, we have already defined. And this is 17, we have already defined all those things. And this is the electric field. This is the absolute electric field can be seen over here. And total current density can be seen over here. Various things can be seen over here, like doping concentration, electric field, in the X direction, electric field in the Y direction. This is the Y direction, this is the X direction, things like that, okay? And if you want to see the energy band diagram, so you have to cut the diagram from source to the drain. Let us do it. So it will be in Y direction, this place over here, and you get this energy band diagram, right? So things like in the vertical section, what it will look like, things can be done in a very good way. Okay? And next, I will show you one more tool. This is known as Inspect. Here you can easily visualize the PLC files. Okay? Here it contains all the IDVG information. So gate voltage output in the x-axis and the drain in the y-axis. So you've got a very nice curve over here. As the gate voltage keeps on increasing, your drain current starts rising exponentially, right? So, right, these things are there. So